Computer science is the foundation of all computing disciplines. It includes an entire range of sub-areas, like machine learning, natural language processing, computing systems, networking, operating systems, AI, and human factors. Computer science focuses on the development and testing of software and software systems. It involves working with mathematical models, data analysis and security, algorithms, and computational theory. Computer scientists define the computational principles that are the basis of all software. Information technology, IT, focuses on the development, implementation, support, and management of computers and information systems. IT involves working both with hardware, CPUs, RAM, hard disks, and software, operating systems, web browsers, mobile applications. IT professionals make sure that computers, networks, and systems work well for all users. Computer science is the study of computation, information, and automation. Computer science spans theoretical disciplines, such as algorithms, theory of computation, and information theory, to applied disciplines, including the design and implementation of hardware and software. Algorithms and data structures are central to computer science. The theory of computation concerns abstract models of computation and general classes of problems that can be solved using them. The fields of cryptography and computer security involve studying the means for secure communication and preventing security vulnerabilities. Computer graphics and computational geometry address the generation of images. Programming language theory considers different ways to describe computational processes, and database theory concerns the management of repositories of data. Human-computer interaction investigates the interfaces through which humans and computers interact, and software engineering focuses on the design and principles behind developing software. Areas such as operating systems, networks, and embedded systems investigate the principles and design behind complex systems. Computer architecture describes the construction of computer components and computer-operated equipment. Artificial intelligence and machine learning aim to synthesize goal-oriented processes such as problem-solving, decision-making, environmental adaptation, planning and learning found in humans and animals. Within artificial intelligence, computer vision aims to understand and process image and video data, while natural language processing aims to understand and process textual and linguistic data. The fundamental concern of computer science is determining what can and cannot be automated. The Turing Award is generally recognized as the highest distinction in computer science. Despite the word science in its name, there is debate over whether or not computer science is a discipline of science, mathematics, or engineering. Alan Newell and Herbert A. Simon argued in 1975. Computer science is an empirical discipline. We would have called it an experimental science, but like astronomy, economics, and geology, some of its unique forms of observation and experience do not fit a narrow stereotype of the experimental method. Nonetheless, they are experiments. Each new machine that is built is an experiment. Actually constructing the machine poses a question to nature, and we listen for the answer by observing the machine in operation and analyzing it by all analytical and measurement means available. It has since been argued that computer science can be classified as an empirical science since it makes use of empirical testing to evaluate the correctness of programs, but a problem remains in defining the laws and theorems of computer science, if any exist, and defining the nature of experiments in computer science. Proponents of classifying computer science as an engineering discipline argue that the reliability of computational systems is investigated in the same way as bridges in civil engineering and airplanes in aerospace engineering. They also argue that while empirical sciences observe what presently exists, computer science observes what is possible to exist, and while scientists discover laws from observation, no proper laws have been found in computer science, and it is instead concerned with creating phenomena. Proponents of classifying computer science as a mathematical discipline argue that computer programs are physical realizations of mathematical entities and programs that can be deductively reasoned through mathematical formal methods. Computer scientists Etzger W. Dijkstra and Tony Hoare regard instructions for computer programs as mathematical sentences and interpret formal semantics for programming languages as mathematical axiomatic systems. Computer science focuses on methods involved in design, specification, programming, verification, implementation and testing of human-made computing systems. As a discipline, computer science spans a range of topics from theoretical studies of algorithms and the limits of computation to the practical issues of implementing computing systems in hardware and software. CSAB, formerly called Computing Sciences Accreditation Board, which is made up of representatives of the Association for Computing Machinery, ACM, and the IEEE Computer Society, IEEE-CS, identifies 4 areas that it considers crucial to the discipline of computer science: theory of computation, algorithms and data structures, programming methodology and languages, and computer elements and architecture. In addition to these 4 areas, CSAB also identifies fields such as software engineering, artificial intelligence, computer networking and communication, database systems, parallel computation, distributed computation, human, computer interaction, computer graphics, operating systems, and numerical and symbolic computation as being important areas of computer science. Programming language theory is a branch of computer science that deals with the design, implementation, analysis, characterization, and classification of programming languages and their individual features. It falls within the discipline of computer science, both depending on and affecting mathematics, software engineering, and linguistics. It is an active research area, with numerous dedicated academic journals. Formal methods are a particular kind of mathematically based technique for the specification, development, and verification of software and hardware systems. The use of formal methods for software and hardware design is motivated by the expectation that, as in other engineering disciplines, performing appropriate mathematical analysis can contribute to the reliability and robustness of a design. They form an important theoretical underpinning for software engineering, especially where safety or security is involved. Formal methods are a useful adjunct to software testing since they help avoid errors and can also give a framework for testing. For industrial use, tool support is required. However, the high cost of using formal methods means that they are usually only used in the development of high-integrity and life-critical systems, where safety or security is of utmost importance. Formal methods are best described as the application of a fairly broad variety of theoretical computer science fundamentals, in particular logic calculi, formal languages, automata theory, and program semantics, but also type systems and algebraic data types to problems in software and hardware specification and verification. Computer graphics is the study of digital visual contents and involves the synthesis and manipulation of image data. The study is connected to many other fields in computer science, including computer vision, image processing, and computational geometry, and is heavily applied in the fields of special effects and video games. Information can take the form of images, sound, video or other multimedia. Bits of information can be streamed via signals. Its processing is the central notion of informatics, the European view on computing, which studies information processing algorithms independently of the type of information carrier, whether it is electrical, mechanical, or biological. This field plays an important role in information theory, telecommunications, information engineering, and has applications in medical image computing and speech synthesis, among others. What is the lower bound on the complexity of fast Fourier transform algorithms? Is one of unsolved problems in theoretical computer science. Scientific computing, or computational science, is the field of study concerned with constructing mathematical models and quantitative analysis techniques and using computers to analyze and solve scientific problems. A major usage of scientific computing is simulation of various processes, including computational fluid dynamics, physical, electrical, and electronic systems and circuits, as well as societies and social situations, notably war games, along with their habitats, among many others. Modern computers enable optimization of such designs as complete aircraft. Notable in electrical and electronic circuit design are SPICE as well as software for physical realization of new, or modified, designs. The latter includes essential design software for integrated circuits. Social computing is an area that is concerned with the intersection of social behavior and computational systems. Human-computer interaction research develops theories, principles, and guidelines for user interface designers. Software engineering is the study of designing, implementing, and modifying the software in order to ensure it is of high quality, affordable, maintainable, and fast to build. It is a systematic approach to software design, involving the application of engineering practices to software. Software engineering deals with the organizing and analyzing of software. It does not just deal with the creation or manufacture of new software, but its internal arrangement and maintenance. For example, software testing, systems engineering, technical debt, and software development processes. Artificial intelligence, AI, aims to or is required to synthesize goal-oriented processes such as problem-solving, decision-making, environmental adaptation, learning, and communication found in humans and animals. From its origins in cybernetics and in the Dartmouth Conference, 1956, artificial intelligence research has been necessarily cross-disciplinary, drawing on areas of expertise such as applied mathematics, symbolic logic, semiotics, electrical engineering, philosophy of mind, neurophysiology, and social intelligence. AI is associated in the popular mind with robotic development, but the main field of practical application has been as an embedded component in areas of software development, which require computational understanding. The starting point in the late 1940s was Alan Turing's question, "Can computers think?" and the question remains effectively unanswered, although the Turing test is still used to assess computer output on the scale of human intelligence. But the automation of evaluative and predictive tasks has been increasingly successful as a substitute for human monitoring and intervention in domains of computer application involving complex real-world data. Computer architecture, or digital computer organization, is the conceptual design and fundamental operational structure of a computer system. It focuses largely on the way by which the central processing unit performs internally and accesses addresses in memory. Computer engineers study computational logic and design of computer hardware, from individual processor components, microcontrollers, personal computers to supercomputers and embedded systems. The term architecture in computer literature can be traced to the work of Lyle R. Johnson and Frederick P. Brooks, Jr., members of the Machine Organization Department in IBM's Main Research Center in 1959. Concurrency is a property of systems in which several computations are executing simultaneously, and potentially interacting with each other. A number of mathematical models have been developed for general concurrent computation, including Petri nets, process calculi, and the parallel random access machine model. When multiple computers are connected in a network while using concurrency, this is known as a distributed system. Computers within that distributed system have their own private memory, and information can be exchanged to achieve common goals. This branch of computer science aims to manage networks between computers worldwide. Computer security is a branch of computer technology with the objective of protecting information from unauthorized access, disruption, or modification while maintaining the accessibility and usability of the system for its intended users. Historical cryptography is the art of writing and deciphering secret messages. Modern cryptography is the scientific study of problems relating to distributed computations that can be attacked. Technologies studied in modern cryptography include symmetric and asymmetric encryption, digital signatures, cryptographic hash functions, key agreement protocols, blockchain, zero-knowledge proofs, and garbled circuits. A database is intended to organize, store, and retrieve large amounts of data easily. Digital databases are managed using database management systems to store, create, maintain, and search data, through database models and query languages. Data mining is a process of discovering patterns in large data sets. Conferences are important events for computer science research. During these conferences, researchers from the public and private sectors present their recent work and meet. Unlike in most other academic fields, in computer science, the prestige of conference papers is greater than that of journal publications. One proposed explanation for this is the quick development of this relatively new field requires rapid review and distribution of results, a task better handled by conferences than by journals. Computer science, known by its near synonyms, computing, computer studies, has been taught in UK schools since the days of batch processing, mark-sensitive cards and paper tape, but usually to a select few students. In 1981, the BBC produced a microcomputer and classroom network, and computer studies became common for GCE O-level students, 11, 16-year-old, and computer science to O-level students. Its importance was recognized, and it became a compulsory part of the national curriculum, for Key Stage 3 and 4. In September 2014 it became an entitlement for all pupils over the age of 4. In the US, with 14,000 school districts deciding the curriculum, provision was fractured. According to a 2010 report by the Association for Computing Machinery, ACM, and Computer Science Teachers Association, CSTA, only 14 out of 50 states have adopted significant education standards for high school computer science. According to a 2021 report, only 51% of high schools in the US offer computer science. Israel, New Zealand, and South Korea have included computer science in their national secondary education curricula, and several others are following. Computer science, a discipline that once lurked in the backrooms of corporate towers, has now burst forth into our lives with an astounding impact. In today's high-tech world, understanding the ins and outs of this scientific behemoth isn't just for the basement-dwelling keyboard wizards, it's for anyone who appreciates the sleek allure of a smartphone, the near-magical capabilities of AI, or the revolutionary potential of blockchain technologies. So, you ask, what is computer science? Simply put, it's the study of algorithms and data structures, how they're designed, how they're implemented in software and hardware, and how they're applied to solve real-world problems. But don't let this simple definition fool you, the essence of computer science runs much deeper than that. It's a discipline that merges creativity with logic, encourages out-of-the-box thinking, and drives our modern world forward. Now, let's sidestep from the classic brick-and-mortar halls of academia and speak directly about a computer science degree. Does it give you a one-way ticket to tech success? Not exactly, but it's a valuable step on the journey. A degree in computer science arms you with the tools you need to tackle the intricate world of programming languages, data structures, algorithms, machine learning, and more. More than the specifics, it instills a problem-solving mindset, a critical tool for anyone wanting to make waves in the tech world. That said, the pursuit of a computer science degree isn't for the faint of heart. Be prepared to embark on late-night coding sessions and mind-boggling math problems. You'll have to tango with Boolean logic and tussle with complex algorithms. But trust me, the rewards can be bountiful. This isn't just about the allure of a generous paycheck, although, let's be real, that's not too shabby. It's about being on the cutting edge of innovation, shaping the technology that shapes our lives. Now, perhaps you're reading this from the heart of the cryptocurrency community, and you're asking, what does computer science have to do with me? Well, everything, my friend. The concepts and practices that underpin computer science are the same ones that drive the mechanics of cryptocurrency. Blockchain technology, cryptographic principles, peer-to-peer networks, all of these core components of the crypto world are rooted in computer science. Understanding the how and why behind these principles won't just improve your crypto literacy, it can potentially up your game in navigating this dynamic digital market. But what about AI and machine learning, you ask? Well, it's computer science that's propelling these fields into the future. By referencing the concept of superintelligence, a term coined by Nick Bostrom in his groundbreaking book of the same name, we can begin to understand the potential trajectory of AI. Bostrom defines superintelligence as an intellect that is much smarter than the best human brains in practically every field, including scientific creativity, general wisdom, and social skills. This vision is underpinned by advanced computer science, and the potential realization of this superintelligence has profound implications for the future of our world. At the end of the day, understanding computer science isn't just about leveling up your tech skills or boosting your crypto knowledge. It's about seeing the world from a unique perspective, understanding the hidden structures that power our everyday lives, and grasping the future potential of the technology that's reshaping our society. So, whether you're considering a degree, or just looking to learn a thing or two about this intriguing field, know that you're embarking on a journey that's far more than just zeros and ones. To sum it up, computer science is not just a degree or a profession. It's an intellectual revolution that's transforming our world. So, step on board and join the ride. You're not just choosing a career, but becoming a part of the new age of tech nobility. Thank you for watching this video.